Awesome. So that's the three of us, and we're gonna be speaking about different aspects of AI applications in engineering. But first, before we go into that, a little bit about our sponsor for today's event, which is LabLinks, essentially the platform we are using for this webinar. So LabLinks is an ecosystem for researchers. The goal of LabLinks is to be able to create this ecosystem where researchers can share knowledge through events like what we're having now, find research opportunities. For example, you're trying to get into a new lab and you're finding it's challenging finding those opportunities either via LinkedIn. LabLinks brings together all those opportunities in one place such that researchers can easily find those and then to connect and collaborate, right? So we are researchers, we want to learn from each other and sharpen our edge. And so LabLinks is this space where you could find researchers that are doing, work similar to yours, and you can connect, collaborate, and publish papers. And if there's anyone listening who is also interested in hosting the event like we are hosting today, you can just email what's on your screen to the left here. Um, Let me just use the pointer. So you can email contact@lablinks.com and use the subject line event, and they would be able to respond to you on how to set that up. What this webinar is about largely today is to give some sort of high level overview of what AI is in civil engineering, where we think the field is moving towards. Um, And to do that, we'll also kind of explain a little bit about sensors, instrumentation, civil engineering data, spend some time on the AI models and the applications that exist to kind of open your eye into what you should be looking at if you're interested in these things. And then we end with resources to get you started. So if you are at the beginning of your journey or somewhere in the middle, uh, these resources are good places to start or reference points to go back to as you continue in your research endeavors. And then we also want to have discussion, right? We want to go back and forth. We just don't want to keep hearing our own voices here. So we want to hear your voice as well, want to hear your perspective on what you think about AI and where the future holds for that. So we'll have that conversation right at the end. Um, so what the high level thing that we need to figure out here for the course of our presentation is the AI landscape. What does it look like overall, right? If you look at artificial intelligence as a broad field, you can break it down into these large subsections. One is the rules-based system. Essentially, you know what you want, like a physics-based system. You know what you want, you hard code those systems and they follow those rules. So you have the logic in your head and you're trying to put that out. So a simple way is if you know something follows a linear pattern, you can write the code such that it follows that linearity rule, right? For machine learning here is you don't know what that underlying pattern is, but you have data that describes a lot of things about that system. And you're using your intuition as a scientist or from domain experience to say, can I learn from this data? And that's where everything is kind of headed today, right? So how can we learn from civil engineering data? That's machine learning as a niche. But then you have other umbrellas of artificial intelligence, such as research and optimization and robotics. Research and optimization is you have essentially a field, a large field that you're trying to optimize or get the best route of. And so within this field, you set your constraints and then you search within those constraints, figure out what your best route is. And then another popular or emerging field is robotics. So up until the significant advancement of machine learning and data-driven solutions, robotics kind of relied on rules-based system, right? You would have to hard code what that robot needs to do, and so it was limited. But with the significant emergence of machine learning and learning from data, we can create some sort of brain for a physical system. So a robot has a body, but it cannot think and act. It cannot perceive independently. So if we make this loop sort of complete, where this physical system is able to perceive, is able to think and act, that's I think that's the pinnacle of AI, right? Given the body. So it's typically called embodied AI in today's world.
All right, then. Going more into machine learning as a whole, like KJ mentioned, it's all about recognizing patterns from data. And you have the classical um, frameworks of being able to learn outcomes from data, which really depend on the kind of data you have. Um, we have frameworks that involve just detecting linear patterns. That's with linear regression. Or if you have non-linear patterns, then you can use slightly much more complex models like decision trees, random forests, vector machines. Or if you want to be able to identify groups from your data, then you can use k-means clustering. Or if you want to be able to identify really complex data, then you can use XGBoost. But you will notice that the classical machine learning really and it really requires some knowledge of the inputs and you trying to tune that knowledge through your data to be able to predict some outcome. Over the years, we've had advancements in deep learning, which allows us to capture patterns from much more complex data like images, like time series, like text. And we have various frameworks as well, which we will go through which we'll go through properly today.
So basically, what these are used for, you have heard about data, about the model, KJ talked about data, and James talked about how we can learn patterns from the data. So what it can actually do is basically different type of application. It can do forecasting. If you take the example of forecasting like tomorrow, what gonna be weather, it can predict that. It can recognize pattern based on existing imageries. For example, you have data about different kind of defects in the road, and you are able to predict what caused that and when it caused that. And then you can also like schedule the project activities and it can decrease the cost. So, with all this fuss about that AI is revolutionizing the industry, we need to focus what AI can do and what it can't. So, if we start about what it can do is basically it can recognize the pattern from this large amount of data, and that pattern can be used for prediction, classification of different kinds of um, issues in the construction projects or in different types of materials. And it can also compare thousands of solutions, and of course, with much faster than humans. So, the value AI is here providing is basically speed, consistency, and scale. Like you can analyze more information and you can also identify the issues that would otherwise be difficult to identify. But being able to analyze information, does it also mean it can also make decisions? So here comes AI can provide option, evidence, and recommendation, but it cannot understand the full situation like an engineer does. It cannot take the responsibility of decision. It cannot make a judgment like a professional engineer. And it cannot understand the community values. What we can do there comes engineer. So we get the outcome from the AI, we compared it with the real world application, our safety standards, our project requirements, and then we make a recommendation. How we going to make the recommendation? We are keep on saying again and again that there is data based on which a machine learning model or anything can make recommendations. Where this data comes from. So in civil engineering, we largely rely on these sensors and instrumentation based on which we get the measurements from the real world applications. For the next slide, I'm showing a video of the building. And the main takeaway here is if you see that there are a lot of sensors that are attached in this building. This building is an industrial building in Saudi Arabia, and they totally like equip the building with the instruments and sensors that can track temperature, movement, action, and different types of operational condition across the building. And it's continuously tracking these activities and updating the information again and again into the system. In this way, you have the track of all the activities that are going on across the building, based on which our team, engineers, and everyone can make any kind of decision or judgment about the building. So the sensors which are feeding this kind of data, it can be different kind of data. It can be temperature data, vibration data, human activity data, and equipment status data. And all these data are continuously being tracked and recorded in some system.
Okay, we've looked at buildings. Let's look at a different kind of infrastructure here. So we are considering bridges now. There's a contrast between buildings. Buildings mostly indoors, bridges you are outdoors, right? So first thing that comes to your mind is physically, this is going to be more challenging than an indoor environment, right? Because indoor you have a lot of controls. Maybe your integrated system has all this pointing to a data storage system. But outdoors, you need to figure out how you wirelessly transmit this information, right? And so for most outdoor system, you are not just thinking about collecting data, you're thinking about how you're going to transmit that data as well. Like you can see the data logger and wireless transmitters here. But these are typical sensors you can find in a bridge for structural health monitoring purposes. For example, you can have strain gauges here that kind of detects if your if there are some small strains occurring in concrete, because we know that uh, concrete is good in compression, but in flexure is really not so good. And so you want to detect if there's some kind of micro cracks emerging. So you have your strain sensors there, you have accelerometers, and typically just to divert a little bit, for structural health monitoring purposes, you have a base state which you compare against future changes. So you've established that baseline. So your accelerometers, your strain gauges, your displacement sensors, all of these are feeding data, right? This is the point. You want to collect as much data about your infrastructure as possible. And again, feed that into your model for your model to process and let you know if something is wrong. So this is an example of bridges. We could also look into dams, which the typical instrumentation here again has to relate to the infrastructure under consideration. So it depends on the infrastructure, right? So you can contrast what we see here to what we had in the bridge to what we had in the building. So the infrastructure determines the kind of instrumentations or sensors that you have there. For example, in this case, you have an inclinometer, you have a settlement plate, because you know that the way a dam would fail significantly differs from the way a bridge would fail. So you might not have an accelerometer in this case here, and you have a piezometer to tell you pressure. You have a way to measure seepage as well. And so the point of this is instead of having regular visits to a dam to check it over time, how can we instrument this physical infrastructure, collect data, build a model that can tell us when something goes wrong? That's the point of applying AI in civil engineering, uh, amongst others.
Now, looking towards an even different type of infrastructure, which we have roads, basically transportation. Roads are pretty very important for moving vehicles, moving people from place to place, and the safety of these infrastructure is quite important. These roads span a huge network, and so um, installing sensors at every point can be a logistical nightmare. And so it's way much more smarter to have sensors that can detect during motion. And so to detect things like cracks, potholes, voids, state of reinforcement if it was a concrete pavement or surface deflection, we have these sensors tracking data in various forms, either as images or either as vibrations. And going further, we have road networks that extend out of towns into cities and into bigger regions. We need to be able to capture data at a much more larger scale, which is where satellite comes in. And so with sensors and satellites, we can track even bigger phenomena like wildfires. We can track floods. We can track oil spills. We can track presence of lakes and efficiently process this to be able to predict much more easily with AI.
Yeah. So we've talked about different ways in which you can collect data from small scale instrumentation to large scale like satellites. When you think about this one thing already comes to mind. These instruments are collecting data in different forms, right? So data in civil engineering is largely multimodal. So let's talk a little bit about engineering data, right? So there are three broad forms of engineering data. There's the structured data, the semi-structured data, and unstructured data. So structured data is, I like to think about it like flexibility, right? For structured data, it's not so flexible. Think of rows and columns of your spreadsheet. So you have a set of features or a set of columns that are there, and then you have your rows, which are like inputs into those features. So you need to have that organized. And if you want to change it, you need to change a lot of things. That's not so flexible. But when you think about semi-structured data and unstructured data, this is where a lot of AI applications in civil engineering rest. We do have for structured data. Maybe you're collecting samples in the lab. Like I did a project a while ago where I was doing some compaction on some soil and collecting moisture content and all of this. That's a structured data. That's stuff you could do in the lab. But imagine you're instrumenting a bridge or a dam or the satellite imagery, like James mentioned. Your data will be largely semi-structured or structured, right? And so for semi-structured data, that flexibility is a little there. It has some organization. Maybe if you think of like a JSON file, right? It has some organization in it, but it can vary. So if I have a humidity sensor and a temperature sensor, the information they capture are different. And so if I try to merge them into a rigid format, I might have some missing values here and there because temperature is not the same thing as humidity. So if I force them into a rigid row and column, I'll have a lot of missing gaps with the semi-structured. The unstructured, just think about images. Like James was mentioning again, if you're driving and you're trying to do a structural health monitoring survey of a road and you're capturing images, capturing cracks, from the picture, you cannot tell if this is significant damage or small damage. We as humans can do that, but it again is subjective, right? So that makes it unstructured. It's highly flexible. So for data, the more flexible it is, the more unstructured it is. Right? So that's how to think about those three broad data forms.
So, as KJ mentioned, like we have structured data and unstructured data. So, under each category, we have, depending on the kind of instruments we are using, we have different formats of data. So, if we start from the tabular data, the same example I will give you is the data in the form in your spreadsheet. If you have worked with Excel spreadsheet or you have worked with material measurements, usually they come in the spreadsheet. You can also take an example of asset measurement or any kind of data that has some kind of parameters on the top and has some values on the bottom. Then we have time series and sensor data. If you go back the video that I showed you, the building that had a lot of sensors. And I told you that sensors are continuously tracking each and every activity across the building. It can be activity corresponding to temperature, humidity, location, activities of any kind of workers, engineer who are working there. Now that data is continuously being tracked. That means that is the recording that's been done over some time period. Anything that's being recorded continuously over some time span is time series and sensor data. These data are in continuous form. They have time as their parameter. Then if I connect that data to certain kind of location, then that becomes a GIS data or spatial data. Spatial means that it will have location, and GIS, like as a whole, what's the procedure to collect this kind of data? And you can take example of land use data or road networks, water, canals across the country. So depending on the type of the instrument that you are using and depending on the problem that you are dealing with, you have different formats of data.
Yes. To even further expand that, like we said, civil engineering data is largely semi-structured and structured. These days, images and videos are becoming a thing since large language models emerged. It's just become more mainstream, right? So think of a camera on a bridge. You want to capture deflections, deformations. Uh, for your roadway, you want to also capture those micro cracks and all of those things. So images and videos are increasingly being used um, in civil engineering, to capture to kind of learn from them. The next big thing is text and engineering documents. So reports. If you go to any Department of Transportation, wherever you go in the world, they generate a ton of reports, right? The specifications, the permits, a lot of stuff. How can we gain insights from these documents? They're largely unstructured. So maybe this goes into the domain of applying large language models to this documentation. Um, but engineering documentation, reports, logs are becoming a big source of information. So as an engineer, if you're thinking of a solution to apply AI to, you need to have these large data modalities in mind. The first thing that needs to come to your mind is data, 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 right? So if you are functioning in any capacity, maybe as a researcher or in industry, you need to think, what kind of data do I have access to? Do I have more images? Do I have more text and document? Because without data, you really cannot do anything. So you need to think first about what you have access to. And then you have the 3D BIM and point clouds, which is emerging over time. But this, because of its cost and the significant technology involved, maybe it's not so widespread, but it's very specific to particular infrastructure. So if you're thinking of a particular bridge that you want to monitor or maintain over time, maybe you want to have a digital twin of that, maybe you use BIM to access that, maybe you use point clouds to get that information. I would classify point clouds as some sort of semi-structured data because it has some structure to it, but spatially it's free form. So it's kind of somewhere between semi-structured and unstructured. Most people will say unstructured, but I personally think it's kind of semi-structured. Uh, having said that, what can all of these forms of data enable? You need to put yourself in the position of the engineer and think, what do I want to do? Am I trying to predict? Am I trying to forecast something at a point in time in the future? Am I trying to spatially map a problem, for example, flood, wildfire, um, any problem that has this locational change, like Fatima mentioned? Am I trying to do that? Am I trying to monitor like a bridge? Do I want to track the changes of this bridge over time so that I get this early warning that something is going to, go wrong? Or earthquakes, that's even a good example of early warning signals with different forms of data. Do you want to do document analysis, digital twin, all of those? So this application of data, AI and data in civil engineering is widespread. It's widespread, and you just need to open your eyes to begin to first assess where you are in your workplace, in your research, and then figuring out what to do with that.
Okay, great. Now we've looked at the kinds of ways we sense data, and we've looked at these various forms of data, and all of this is what AI deals with. And so we want to see how AI reasons and adapt over these various forms of data. I would start off with this broad overview of kind of like the major kinds of AI tech we have today. It's there are so many, there are much more subdivisions, but you can remarkably talk of computer vision, we can talk of predictive analytics, we can talk of generative AI, or even down to advanced robotics. Going off of computer vision, lots of the kind of data we have to do with images. And these images have various properties in them: color, shape, size, structure. We have sets of models in computer vision called convolutional neural nets that can detect these features. And so if you have images, for example, in construction, during construction, or images of sites or video feeds, like the possibilities are the possibilities of what you could have as features are very expansive. And being able to capture these details can let you do so much types of predictions. So, for example, we could go into identifying vehicles from uh, imagery footage, traffic footage, which can help in further downstream tasks in transportation modeling. It could be identifying structural types during construction as well. It could be even identifying faults in places where it's really a logistical nightmare to sense faults. Here, for example, sensing faults in sewer pipes. Also, we also have other forms like numbers that we collect, structured data that we collect from our experiments or our sense of what we sense. Uh, Now, lots of these numbers usually have relationships, things like trends, things like correlations. And so we have various kinds of machine learning models that can identify these trends and patterns. A very useful application could be things like forecasting, which could which could be in forecasting, say, when a particular material, say pavement, is gonna experience fatigue, or even coordination, things like project delay or how you allocate resources. And so going off some example here is this Google uh, latest release of GenCast, which is used for forecasting the weather. It's so subtle, but the amount of processing that it takes to have accurate weather for tomorrow or the next 1 hour entails processing physical models and using huge supercomputers. But with predictive analytics, with being able to capture trends and patterns and being able to calibrate, we have tech for detecting weather much more accurately. Also, we can detect water networks from pipe networks. For example, there's here in this Jacobs project, being able to determine locations of various stormwater infrastructure, and also maintenance and overall analytics for our infrastructure systems. Also, we have generating generative AI. So lots of the other types of AI applications we have require explicit inputs. You need an explicit image to be able to classify a car. Um, if you imagine that cyclic system, it means that to be able to have better AI models, we would need much more and more data. But with the patterns, with the core way you can learn patterns from data, we can do that to generate more data. And so you typically depend on conditions or like constraints, like oh, like what materials, what physical setup or costs, to generate data. And so it could be in various applications, say in a structural form. This is an imagined field in AI and in civil engineering. Especially, of course, we have BIM models, all established, but to be able to generate structural designs for electrical systems or mechanical systems um, or everything that we have to do with CAD files, which will require intensive modeling, can be generated from conditions.
You want to play that?
We can just skip over that period of time.
Okay. Here I'm just going to talk a little bit about embodied AI, right? So up until this point, we've talked about models that live somewhere that you don't particularly see. Maybe they're in the digital space, maybe they're on your computer. So you have this model somewhere. Everyone is talking about models, but no one sees the model, right? So this embodied AI is a manifestation of artificial intelligence. We have the brain already, the AI that we've trained that can perceive information, that can think because it has a processor inside of it, and then we give it a body to act essentially. So here we want to make something in our own image, like a human. We can perceive with our eyes, our ears, we can think with our brain, and we can act with our muscles, our hands, essentially. So that's where the future of AI lies, amongst many things, but this is kind of where it's heading towards in civil engineering, because you want to be able to not just design and act in your office, you want systems to be able to assist you in the field. And so embodied AI is kind of broken down into two parts. There's this whole part that we've talked about, which is collecting data and train the model. Uh, but there's also the second part of it, which is giving it a body, giving it a way to act. And this is where computer science meets robotics, right? How can I actuate an arm? How can I pick this up? How can I control that? And how can I sense information and process it in real time? And depending on the kind of model that you use, how can I learn from new information over time? So this is kind of a loop. It's not like once trained and done. It's like it continuously improves as it perceives its environment. And I'll give you a video of a typical example here that was just published. So this work was just published not too long ago. This was done in Germany, where a robot is trying to decommission a building. So we typically have, when a building has reached the end of its life, you want to break it. Kind of explosion is the typical way to do it. Right? You just explode the entire building. But what these researcher did was that they developed some robot that's able to perceive, sense, and autonomously decouple what a building is. And what this helps with is that you can recycle the material. So instead of blowing this into bits and then you just end up throwing all of this in a landfill, you can break it into bits carefully, just the way you build it up carefully. And then you can take all of these pieces, recycle it, and use it. So this is a good example of where the field is headed. There's also an application of the Boston Dynamics team, their dog called the Spot. It's called Spot, right? So this dog now they work together with a company called Trimble, which is a civil engineering company as well. And what Spot is able to do is that on the field, it's able to roam freely, just the way your dog would roam freely. It's able to roam, scan the site, monitor construction progress. So now you don't need someone filling up a log, right? Spot is able to do that. It's able to give you survey data about your land. It's able to monitor for safety hazards on the field, on the site, and report it. So Spot is able to do a lot of things. So this eliminates a lot of managers from the field. So managers should be worried about emerging technologies like robotics. Okay, so this is where we think um, the future of AI in terms of civil engineering is heading. Uh, but before we go to the next session, before we start there, I think I have a question to ask, which is for those people who are attending, can you think about where you are in terms of your workplace and figure out what's that thing that I can apply artificial intelligence to, right? And I'm asking this question because we're going to, after the session, we're just going to move straight to a little bit of discussion. Uh, and then in the discussion, you can share with us your opinion about where you are, what you're doing, what aspect of application of AI in civil engineering you think applies to your work, maybe how you need help, maybe your own perspective of what AI can do in civil engineering. So I want you to think a little bit about that before we head into discussion. So, James.
Okay, great. And just to cap this off, we'll look at getting started or what you need, uh, pointers, resources to help you with working with AI. Um, you could have you could be here with various knowledge levels. You could be totally new to this. And so if you're new to this, it would be great to have some knowledge of foundations, fundamentals for machine learning or deep learning or these other applications, which you can find at various institutional courses. If you want to go much more specific, there's the emerging field of scientific ML, where we're also, apart from dealing with understanding patterns in data, we're trying to ensure that these AI models behave in physically realistic ways. And so there's this aspect where you could go into as well, or you could look into AI applications for your specific domain. For example, climate change workshops, conferences or hydrology tutorials that have pretty established AI models for doing workflows. And then there's also the geospatial world of dealing with geospatial data and running AI models for them. And tools you typically need will be programming uh, with Python or JAX, and a couple of standard packages like NumPy, Pandas, Scikit-learn. These are just fundamentals that are used at the various workflows, the various components in the pipeline of working with AI. And yep.
So, like today we discuss what's the application of AI in the field of civil engineering, and we started from what is basically artificial intelligence, its branches like machine learning, deep learning, robotics, and then we discuss the fundamental part, like where we can get the data to get all the to take all the informed decision about any kind of problem. So this was our perspective where AI is standing and what are its capabilities, what it can do, and what it cannot do. But now we want to know your opinion that where, like in the field of civil engineering, AI is heading towards. Is it like something that we feel like it can take decision on our behalf, or it can help us as a tool? And we also want you to, like, we will appreciate the questions, like if you have any kind of ethical consideration, because in the field of civil engineering we are largely working with ethical codes, community values, standards, safety, and real world problems. And is there any kind of limitation in collecting this kind of data that can be a constraint towards fully applying AI in the field of civil engineering? So just feel free. I'm just bombarding with the questions. So anything, like if you have any opinion towards it, just feel free to ask any kind of question.
Yeah, and to add to that, just before most of you joined, we talked about having subsequent series. So this is very preliminary discussion to give you a bird's eye view of what AI in civil engineering looks like. Would like to get your feedback uh, so that we know what the next potential series should be. So maybe you're here, you're familiar with the domain a lot, but you probably want to see something specific on artificial intelligence in maybe safety or flood risk or contaminant tracking, where we go deep into showing you what a model looks like, how to write the code for that, maybe some short tutorial on that. If that's your perspective, you can share it as well. Um, and if you'd also want to co-host with us, we invite you to share to contact us personally, and we can have you also on the next series, and you can talk about your work. But for now, I want to hear from you, so feel free to raise your hand. Um, if you don't know what that is, it's a small icon of a hand raised right on your screen. You can click on that, and then we can bring you up stage, and you can share your perspective and ask any questions you want.
You can also give us feedback, like when the seminar gonna be over. Even if you have any question or recommendation or comments, you can also just send us directly on the lab links or
Questions. We're ready for anything you have to say. um, or you can just tell us what you're doing now with regards to use of AI in civil engineering. So you can tell us what you're doing, and we can have that back and forth. So we have about 7 minutes more. So I believe we can use that to network a little bit. So you can just raise your hand. We'll bring you up stage. We get to know you. You get to know us, and move from there. Hand raise. Looks like everyone understood everything, and you're all content with what we've said. Looks like no one wants to say anything. Interesting. We already spoke with some people before now, so that's fine. Can I ask Emmanuel? Can you can you share a little bit about yourself with us?
you need to raise hand before we bring you to the stage.
There is an icon at the bottom that says raise hand. If you click on it, we'll be able to bring you up, and then you can share with us. What about Solomon? You have something to share with us? Oh, Emmanuel.
I think we lost the contact.
Yeah. All right, all right. Thank you very much for joining today. Feel free to send an email to contact@lablinks.com, and we'll be able to share more information that we have from here. Connect with us on LinkedIn. You can search any of our names on LinkedIn and connect with us. And we're happy to, take the conversation from here there.
And do share your opinion with us, like for the next seminar in this series. Do you want hands-on experience? Do you want to see example, like how we can use the data that is existing right now we to apply in different applications of civil engineering? We can give you a quick hands-on tutorial as well.
Yeah, if you connect with us and you let us know, maybe data set is your issue because data is a big deal here.
Yes.
So if you need help on, where to get data, what kind of data to look out for, you can also just connect with us. Let us know. We can point you in the right direction. And whatever resources you think we can help you with, feel free to reach out.
Yeah.
All right. Thank you very much, and enjoy a good rest of your day.
Bye.
Cheers. Bye.
Bye.